In this session, we'll discuss the topic eigenvalues and eigenvectors. Eigenvalues and eigenvectors. You can expect questions on this. So let's see. There is a matrix eigenvalue problem, which is also known as simply eigenvalue problem. So it is a vector equation that is a times of x is equal to lambda times of x, where a is given square matrix, lambda is a scalar which will be known as eigenvalue of a, and x which is the eigenvector of a. Geometrically, if we see this ax is equal to lambda x, it means like this x is an eigenvector. Let's say this is a vector. Lambda is a scalar. So if we multiply a vector with a scalar, it will simply change the magnitude of that vector, but the direction will remain same. So the point is, matrix multiplication of this eigenvector x, this a is the matrix, so matrix multiplication of this eigenvector gives a vector which is in the same direction as the original vector x. Or you can say that matrix multiplication does not change its direction. It is in the same direction as the original vector x was. So that is the geometrical meaning of this, right? So from this equation ax equal to lambda x, we can write ax minus lambda x is equal to 0. Now you know this a is a vector, matrix, and lambda is a scalar. So we cannot do this operation. The only possibility is we can write a minus lambda times of I. So I being the identity matrix of the order same as the matrix A. Now this is possible. This operation is possible. This is lambda times of identity matrix, which is subtracted from A matrix. So this is the eigenvalue problem. And if you see, this is nothing but homogeneous equation. This is a homogeneous equation. And this homogeneous equation will have non-trivial solution. What is the trivial solution here? The trivial solution is that the x becomes 0. And for homogeneous equation, in order to have non-trivial solution, we need that the matrix should be singular, so that the rank of that matrix should be less than n. So what is the matrix here? The matrix is not A now. The matrix is A minus lambda times of I. So for A minus lambda times of I to be singular, in order to have non-trivial solution, what is the requirement? The requirement is that determinant A minus lambda I should be equal to 0. And this is nothing but characteristic equation. This is nothing but the characteristic equation. And roots for this characteristic equation gives the eigenvalue lambda. So these roots are known as latent root also, spectrum also. The set of eigenvalues of A is known as spectrum of A. So let's see one example and we'll understand what is it. Determine eigenvalues and eigenvectors for A equal to -5, 2, 2, -2. So what is this eigenvalue problem here? A times of x is equal to lambda times of x. Let's see what is this. This is -5, 2, 2, -2 times of, let's say, x1, x2 is equal to lambda times of x1, x2. And the characteristic equation is A minus lambda I equal to 0. So this can be -5, 2, 2, -2 minus lambda times of 1, 0, 0, 1. Both are of order 2 equal to 0. So that is -5 and minus times of lambda. So minus lambda. There won't be any element here because lambda times of 0. So this will become directly 2. 2. This is 0, so simply 2. This is minus lambda. Lambda into 1. So -2 minus lambda equal to 0. This gives a polynomial equation in terms of lambda of the order 2. The equation will become lambda square plus 7 lambda plus 6 equal to 0. This is your characteristic equation. A polynomial of order 2 in terms of lambda. Right? You can see if the matrix is of order 2, you can expect a polynomial equation of order 2. So if a matrix is of order n, you can expect a polynomial equation of order n in terms of lambda. Right? And the roots for these equations are, you can factorize or using any method you can find that lambda will be equal to -1 and -6. These are the eigenvalues. So we have -1 and -6. And using this A minus lambda I, we can say -5 minus lambda 2, 2 -2 minus lambda times of x1, x2 should give you 0. I'm just putting this again, so we'll see how to use it. So we have two eigenvalues here, -1 and -6. Now we can find the eigenvectors. So let's see. Eigenvectors for lambda equal to -1. From this equation, a minus lambda times of x, lambda times of I, x equal to 0, we'll have to substitute -1. Just now we saw this, so we'll put this -1 here. This is -5 minus of -1. This is still 2. This is also 2. This is -2 minus of -1. x1, x2 equal to 0, 0. Which makes it, this will become -4, 2, 2 and -1 times of. So what is it? If we split it into the different equations, we'll get -4 times of x1 plus 2 times of x2 equal to 0, and 2 times of x1 minus x2 equal to 0. These are the equation we are getting from this equation. And this gives x2 is equal to 2x1. So the eigenvector which is x equal to x1, x2 can be written as x1 and 2x1. Considering this x1 to be scalar, we can write it to be k and 2k, and we can take this k outside and write 1 and 2. So we can say the eigenvector, I'll say EV1 is nothing but 1, 2. Of course, you can write 2 and 4 also. You can write 0.5 and 1 also. You can write 0.25 and 0.5 also. But in general, we are writing it 1 and 2. This k is being any scalar, so we can have all, like we can have 1 and 2 if k is equal to 1. If k is equal to 2, this becomes 2 and 4. If k is 0.5, this becomes 0.5 and 1. If k is 5, this becomes 5 and 10, and so on. So this is the eigenvector in general which you are getting if considering one of the vectors. Similarly, for lambda equal to -6, we'll see what we get for lambda equal to -6. So for the same equation, a minus lambda I x equal to 0, we can put -6 and we'll get, I'm directly writing this, we'll get 1, 2, 2, 4 times of x1, x2 equal to 0, 0. Now this gives you x1 plus 2 x2 equal to 0 from the first set, first row, and 2 x1 plus 4 x2 equal to 0 from the second set. So we can say that x1 is minus 2 x2. These are the equation, and this is the relation from both the equation, conclusion from both the equation. So the eigenvector will be, eigenvector for lambda equal to -6 will be nothing but let's say x minus 2x2 and x2, and of course we can take it out. Maybe you can take k outside and write it minus 2 and 1, or you can also write it k dash as 2 minus 1. These both are the eigenvectors. Let's say eigenvector 2. So any of it is okay. This is also fine, this is also fine. So this is how we can find the eigenvalues and eigenvector. So in general, let's see some of the points. In general, for a matrix n cross n, we can expect characteristic equation to be a polynomial of order n in terms of lambda, right? So there are possibility that we may have at least one eigenvalue. So that is one root of this equation, characteristic equation, or at most n numerically different eigenvalues. Fine. And if, continuing the same, and if we have n distinct eigenvalues, then we'll have n linearly independent eigenvectors. This is eigenvector. So if you have n, like for n cross n matrix, we can have n numerically different eigenvalues, and if we have so distinct values, then we'll have the eigenvectors to be n linearly independent vectors, right? Now there are some more points, properties. It says trace of the matrix A will be nothing but sum of the eigenvalues, and determinant of A will be nothing but product of eigenvalues, right? So this is the sum of sum of the diagonal elements will give you the eigenvalues, sum of the eigenvalues, and the determinant will give you the product of it, product of the eigenvalues. Also, if we say, if for A the eigenvalues are, let's say lambda 1, lambda 2, and so on, lambda n, then for A transpose the eigenvalues are same, lambda 1, lambda 2, lambda n. So the eigenvalues for A and A transpose are same. But if we have A to the power of k, the eigenvalues are going to be lambda 1 to the power of k, lambda 2 to the power of k, and so on, lambda n to the power of k. And if we have A inverse, we'll have the eigenvalues to be 1 by lambda 1, 1 by lambda 2, and so on. So the eigenvalues are being inversed. And if it is multiplied with a scalar, let's say k times of A, the eigenvalues are going to be k times of lambda 1, k times of lambda 2, and so on. Next point is matrices and its eigenvalues. So if the matrix is, say, Hermitian if it is a complex matrix, or symmetric if it is a real matrix. So Hermitian matrix if it is a complex matrix, symmetric matrix if it is a real matrix. Then the eigenvalues are going to be real. And if the matrices are skew Hermitian if it is complex, or skew symmetric if it is real. So skew Hermitian if it is a complex matrix, or skew symmetric if it is real matrix, then the eigenvalues are purely imaginary or zero. Also, if the matrix is unitary or orthogonal, then absolute value of eigenvalues is 1. So whether it is unitary matrix or orthogonal matrix, we'll get the eigenvalues with absolute value being 1. Next point is, for triangular or diagonal matrix, the eigenvalues are the diagonal elements. Why so? Because the trace will give you the, like, let's say if we have 2 0 0 3 for a diagonal matrix, then sum of this is giving you the sum of the product, sum of the eigenvalue, and product of these two is giving you the determinant, which is going to be the product of the eigenvalues. So sum of like 2 plus 3 gives the trace, which is sum of the eigenvalues. 2 into 3 gives the determinant of the matrix, which is the product of the eigenvalues. So ultimately you'll get 2 and 3 to be the eigenvalues. Similarly, if you have a triangular matrix 2 0 1 3, in this case also the sum is going to be 2 plus 3, trace of the matrix, and the product determinant is going to be 2 into 3, because 1 into 0 will give you nothing. So again, in the same case, in this case also the eigenvalues is 2 and 3, that is the diagonal element. And one more important point is, for A, that is n cross n, if it has n distinct eigenvalues, then the eigenvectors formed will form the basis for Rn, or you can say it spans the n-dimensional vector space. If you want, you can say that also. It will span the n-dimensional vector space. So the condition is, if we have for n cross n matrix, if we have all n distinct eigenvalues, definitely the n will have n different eigenvectors which will be linearly independent, and they will form the basis for the n dimensional. Like we have seen in the vector space, that n number of vectors which are linearly independent forms the basis for the nth dimensional vector space. So that applies here also. So that will be all about eigenvalues and vectors, the properties, and the relation. We have to use everything, and there will be very good questions on this.